Hi, I'm Ray from Data Science Rebalanced. We build data science tutorials to help bridge the gap between academia and industry. Today, we're going to briefly talk about behavior-driven machine learning. Let's say you want to build a machine learning model. The first thing you're going to need is a labeled data set. From there, we can push this data through a training pipeline. And on the other side, we end up receiving a set of model parameters. So, how exactly was I taught to do this in school? Well, I was usually given a data set, like we see here, representing a binary classification problem. Here we have two colors representing each of the two classes. And in school, I would have been taught to use all of the data. Literally, take every single bit of the data, split it into a training and test set. But there's a problem. Not all data is created equal. When I look at this data set, I can actually see that some of the data points are more valuable to me than others. These data points in particular are the most valuable data points in this data set. So exactly how do I do this now that I'm in industry? I think of my data set as a collection of behaviors. And I'm trying to use an iterative process to extract all of the behaviors from my data set. Now you might look at this and say, well, Ray, just, randomly sample the data set. And while that seems like a valid technique, there's a problem. Randomly sampling a data set can increase the bias in that data set. For example, let's say that we have a region that is densely packed with data points. If we randomly sample our data set, we will end up capturing more data points from this region than the more sparse regions of the space. What this means is that this region gets overrepresented, i.e., we basically introduce more bias. So instead, we're going to actually cluster our data set. And when we cluster our data set, we can now select, let's say, 3 data points from each cluster, represented by the 3 green dots in each one of the clusters, and we can use that as our initial training set. This training set goes into our pipeline like before, and we get our first model. This model is represented by the red line. Everything above the red line, the model thinks should be a blue dot. And everything below the red line, the model thinks should be an orange dot. We can clearly see here that there are a few situations where the model has gotten it quite wrong. So how do we fix this? Well, if we think about it, the red line actually represents where the model is confused. This would be equivalent to a 50% confidence score. So what we want to do is actually pick data points around the red line, around this 50% confidence range. If we take those points and add them to the original green set of data points from our first training set, we can now train up a new model. This slightly larger data set gives us a better model than before. If this was our first model, this is our second model. Much better. Now we don't have to stop there. We can select a new set of data points from around our area of uncertainty, and we can rerun the process all over again. Now we can go from model 2 to model 3. Slightly better that time. Now in the real world, we would likely run like 100 iterations versus just 3. Every single time we'd add a little bit more data onto the training set and build a fresh model. Now you can pick any decision metric you want, F1 accuracy, precision recall, whatever your favorite. What you should see is that for each model that gets built, you get slightly better performance every single time. Well, up until a point, represented by our black dot. This is where your model is the best it can possibly be using the data that you have available. Once you start adding data on past this point, the model performance actually starts to drift down and get worse. So what is this bias? First, if we have a labeled data set, it helps us build the best model possible. And if you're using all of the data, you're not building the best model possible because some of that data is frankly noisy. Secondly, if you have an unlabeled data set, this is going to save you lots of time. because you don't need to label the entire data set. Thirdly, like we've already discussed, it helps to reduce bias that would come from using the entire data set or just a randomly sampled data set. If you have any interest in this topic, it's often referred to as active learning in the academic community. But there's also a lovely book called Human in the Loop Machine Learning by Robert Monarch. For any data science tutorials or lessons, please reach out. We have a link tree sharing all of our articles and Skillshare courses. Or you can reach out to us via LinkedIn or Gmail.